So this is about our time expanded network exact algorithm for solving escape interdiction games. And this was supervised by Andreas. So I'll get stuck into it. So the outline for this talk is I'm going to motivate what an escape interdiction game is, so EIG, and define it. And then we're going to look at discretization, so sort of making it more tractable to find Nash equilibria, compute Nash equilibria. And then we're going to actually see how we're actually going to compute these Nash equilibria. And we're going to compare various algorithms that have been seen in literature and also produce our own. So here's the setup. So we have some road network, some city, and we have some, say, criminal or suspect who's just committed a crime somewhere. Police are called, and this criminal person, he wants to escape somewhere. So we're just going to denote that with this vertex over there, just sort of on the outskirts of the city, say. And at the same time, there's police, say, like on standby or maybe at some police station or patrolling, and they have various starting positions in the area. And there's a road network, so you can go various directions along each road. And there's intersections, say, and each road, say, takes time to travel. And so the question is, two outcomes. First of all, no interdiction can happen. So an interdiction is sort of when the police can capture the robber, the criminal. And so no interdiction means the robber safely escapes to their target node, the infinity, or they can get captured by the police. So an interdiction happens. I'm sort of lying a little bit. So technically, another thing that could happen is the robber could evade indefinitely, but we're just going to ignore that, and we're just going to say the robber really, really wants to escape. He won't have it any other way. He wants to either escape. He doesn't want to endlessly roam the city. So the question is, how should the attacker, so the attacker in the literature is the common name given to this guy over here. The attacker is the criminal. How should they plan their routes? And on the other side of that, how should the defender, so the police force, together, like sort of as a team, try and capture, try and interdict the attacker on their way? And so this is naturally modeled as a game. So in fact, it's a two-person zero-sum game, which is nice to study it. And so we will be talking a little bit about some game theory in between the slides here, just so that everyone's on the same page. So very natural definition is I have strategy spaces, so the set of all possible strategies I can pick for both players. And then given any pair of strategies that I pick, there's going to be some payoff. So in our case, it's either going to be 0 or 1. 0 meaning no interdiction occurs. 1 means that an interdiction does occur. So, and you can always think of the payoff as sort of the probability of interdiction. We'll get into mixed strategies later. And the payoff, the attacker wants to minimize that probability of interdiction. The defender wants to maximize. And very common solution concept to Nash equilibrium is basically so a pair XY where if you assume that the other player is going to stay playing Y, then there's no better strategy that you can pick as X, and also the other way around. So flipping the roles of X and Y also works there. Okay, so that's that. And here's the more formal definition of escape interdiction game. We're going to have some weighted directed graph, G. We're going to have some time horizon. So we're going to actually ask that the criminal, the attacker, escapes within that time horizon, that T max number. Fix some vertices as so. And we're also going to allow different speeds for the attacker and defender. And also note, we're going to allow, we're going to ask that every single sort of police person have the same speed, but they could be different between the police people and the attacker there. And all of this is pretty much all you need to sort of set up the game. We call all of this the data of the EIG. And so an attacker strategy is a sequence of states. So think of these as you're in a place at a time, and it's very natural. You're starting at time 0. You must end at your v infinity node within the time frame, and then so very naturally, your next node, if you're traveling along vi to vi plus 1, that arc, that edge, then you can only arrive at your next node given your speed here. So you can think of the right-hand side as what's the quickest time I can get to my next node, vi plus 1, if I'm coming from vi. And so notice here, I'm allowing an inequality here. So I'm allowing the attacker to actually slow down as much as they want along an edge. But they cannot travel faster than their sort of maximum speed given by that SA number. So a priori, this is an infinite strategy space. There's infinitely many possible strategies, which is probably not as nice to deal with as for a finite strategy space, which you may have seen in other games. And so on the other side, the defender, very similar, but now the sequence is they're going to allow waiting at a node. So instead of just always arriving at a node and leaving, they're going to allow we're going to allow that they wait at a node for some time interval. So once again, every single police officer has to start at time 0, and they go to some other node. And also importantly, I'm not allowing them to step onto the v infinity node, because that would be sort of cheating. You could always just step on the v infinity node and just wait there forever. I'm not going to allow that. And then for each sort of edge that I traverse, I'm again like restricted by the fact that I have to travel within my my speed there. But notice, unlike the attacker here, the police always go at max speed. If you think about it, it doesn't make sense for police to not go at max speed because they want to always spend time occupying nodes rather than traveling along an edge. So it never makes sense to travel slowly as a defender. So always an equal sign over there. But the sort of continuous infinite strategy space comes into play here. So I'm allowing the waits time to be, in fact, an interval, some real interval that they spend at a node vj. So always max speed there. And then very naturally, an interdiction occurs basically when some police person is on the same node at the same time as the criminal, the attacker. So very simple there. That's when an interdiction occurs. So hopefully that's okay for everyone. We'll look at an example just to get our heads around that definition. So here's my graph there, very simple, small graph. I'm going to set those as my parameters there. There's only going to be one resource R. And so resources you can think of as the individual policeman. But the defender sort of takes care of all the resources at the same time. So here I'm only allowing one police. So the attacker strategy, one way they could do it is they travel along that bottom edge, takes 2 units of time because they have speed 1, and then move up. So that's one strategy. Defender strategy, they could, to interdict that, they need to be on that node U at time 2. So they can do that there. But you may also see there's another thing that another strategy that the attacker could do. They could move up and across. But in order for the police to stop that from happening is they need to be at this node occupying at time 1 here. So time 1, this is enough because of that Tmax is equal to 3 there. There's sort of no slack to sort of play with for the attacker here. So this strategy, this defender strategy, it's a winning strategy. It will always interdict the attacker no matter what they do. So here is sort of the scenario played out. with these two strategies, you can see that the attacker, the red sort of dot, gets interdicted by the police in this strategy there. And even if the attacker went up, they would get interdicted because this edge is only travel distance 1 here. But he still has to reach the infinity within time 3, so he can't go any slower. So there's that. But what if I sort of bump up that T max a little bit, so to 4? So now there's a little bit of slack to play with. And now, if you think about it, these are sort of the essential strategies that can be played. So either the attacker can go along the bottom and then go along this edge over here, or the attacker can go along this vertical edge first and then move up along the right here. So there's those strategies there. And also notice here, the attacker, time 2 is really special to them because by ensuring that the attacker is at different places at the same time too for different strategies, it means the police, he can't capture both of those attacker strategies. The police, he has to choose one or the other. So these two strategies there, they also respectively interdict those ones, and you can see, you can convince yourself that in fact that's our payoff matrix. So columns and rows, very natural. There's an interdiction if y1 goes up against x1 and so on and so forth. But a Nash equilibrium is what we want. If you think about it in pure strategy, so if I am forced to pick one or the other, there is no Nash equilibrium here. But if we go to probabilistic strategies, mixed strategies, then there is a Nash equilibrium. So very natural. Instead, you pick probability distributions over your strategy set. And then same definition as before, Nash equilibrium. If you assume the other person doesn't change their strategy, I cannot benefit by changing my strategy. So that would be Nash equilibrium there. And so in this case, the equilibrium value is 1/2. Both players can guarantee 1/2 probability of interdiction. So the defender, the police, can guarantee at least 1/2 by playing their strategies. And on the other side, the attacker can guarantee at most 1/2 using their strategies. So, and that's enough to show it's a Nash equilibrium. They can both guarantee the same value from above and below. So another example, this is a bit more involved this time. Here's my Tmax and speeds, all distances are 1, so that's fine. So the attacker strategies that are important here is to sort of informally move along one of these rows. So there's sort of 4 rows here. Turns out you don't have to care about these diagonal edges for the attacker. It's enough to consider only these row sort of strategies. And the defender sort of has 2 types of strategies. One where this police up here, it just moves sort of diagonally along this entire diagonal, sort of like a bishop in chess. And they sort of spend 0 wait time at each of those nodes, and they can interdict each of those row strategies that the attacker would do for those 3 bottom rows. And then I don't really care what the second police officer does, because I'm already sort of interdicting all of those strategies already with the first guy. So this guy, the second police officer, it doesn't really matter where they go. The other kind of strategy is, well, the first resource, the first police, can just wait up here at U11, and then the other guy, he can sort of probabilistically 1/3 to each of those rows here, and just wait there instead. And if you think about it enough, this would be the payoff matrix that you come up with. And it turns out this is also or this gives a Nash equilibrium. So you can find out what the Nash equilibrium is for this strategy matrix there. So now we're going to talk about discretization. So how can we actually make it tractable to sort of compute these Nash equilibria? The idea is we're going to fix some smallish real number, in principle real number, but it's really going to be rational or 1. And for the defender strategies, remember in the original definition, we're allowing sort of any interval length wait time, but now we're only allowing for the police to wait for an integer amount of that delta parameter. And also, yeah, the attacker strategies are not explicitly discretized in this. I'm only formally changing the defender strategies. What defender strategy space is allowed here. So another fairly natural definition for game theory is dominance or domination. Basically, a strategy dominates another if it's always better to pick your original strategy Y. So very natural for both players. And remember that these inequalities are the other way because one of them wants to try and maximize, one of them wants to try and minimize. So finiteness of strategies, it's fairly obvious that the defender strategy set is now finite. But also because of the defender strategies as finite, I can also sort of get for free that my other, my attacker strategy space is also finite. And sort of the intuition is, or the other guy, he only has finitely many possible strategies, finitely possible many plays to make. From my space, I only need to consider finitely many to sort of counter against the other guy's finitely many choices there. So that's the intuition there, and we can sort of explicitly construct what strategies the attacker needs to care about. So first of all, very simple idea is we can always scale time by any amount, and in particular, if we have a rational EIG, then we can always get an integral EIG. So very simple. If you go back to the example we had before, we can always just plop a lambda in front of pretty much every single time-related object, and then we get a pretty much the same EIG. The scenario plays out in the same exact way, except we've just scaled a time. So we can pretty much assume integral data if we start off with rational data EIG. And so integers are nice to work with, arguably. So I can now assume, now consider all those strategies that sort of are tucked between the integers. So I just sort of pick half integers because right smack in the middle. And then so clearly this set is now finite. The set of all half integer strategies is finite there. And so if you wanted to explicitly construct how can I, from some arbitrary strategy, pull out some equivalent, or at least dominating half integer strategy, I can do it as follows. So I have some strategy, I pick some minimal j where I finally get some slack. So this is just technical details here, but I can follow this formula and I can come up with a strategy that is a half integer strategy that dominates my my original strategy here. So that means any defender strategy, which remember only occupies for integer amount of times and only leaves nodes at integer times, this will always dominate that one. X dash will dominate X. So here's sort of an example. If I imagine the bottom here, so here's my sort of arrival times at each of the nodes in my original strategy. In this case, my magic J is 1, the J up here. And so I can get my, I can get my times, my half integer times at the bottom, like here. sorry, there's a zoom thing in the way, I can't really see that. So yeah, fairly simple construction. You can just use that formula there. So we have finite strategy space. And so famous theorem of Nash is that Nash equilibria will always exist. So given these this finite set of attacker and defender strategies, I can get out a Nash equilibria. So a little on the side, so sort of the comparison between this this discretized version of escape interdiction games and the actual continuous version is that a discrete optimal Nash equilibrium may not always be a continuous optimal Nash equilibrium. So there is some still some structure that the discretization doesn't really touch, or not directly touch. And so we can actually come up with an example where this is explicit. So in this example here, we do have a continuous optimal Nash equilibrium, and it does have an infinite support for the attacker, but there is no finite support Nash equilibria for both players in the continuous case. So here I'm forgetting about the delta discretization. I'm just dealing with the continuous time escape interdiction game. And so my continuous Nash equilibrium is, well, my defender strategies, I can just sort of send them to the first column, so probabilistically half-half, and just wait there forever. There's only two strategies there, but the attacker strategies here sort of are along a whole entire continuum. So here's where the continuum is. So for every single tau within that time interval, I'm choosing to arrive at my sort of first column, my U here, at time tau, and then move on to the next column at time tau plus 1. And so I'm sort of playing the uniform probabilistic strategy there. And so both players can guarantee 1/2 with each of their respective strategies here. So that does form a Nash equilibrium with infinite attacker support. But the reason why, we can go through the reason why there doesn't exist a finite support Nash equilibrium under the case where it's a continuous game. So the finite defender strategy X before, that's completely fine. That guarantees at least 1/2. So it's just going to show sort of by contradiction that no finite support attacker strategy can guarantee at most 1/2. And so by contradiction, yeah, you can assume that there is some strategy that satisfies that. Because it's finite, there is some final time, t, that the attacker will leave that first column. And it is played with non-zero probability. So there is a final time that the attacker leaves that. And so I can sort of, supposing that I have a Nash equilibrium, I can change my X slightly to, instead of just staying at my first column forever, I can leave at the last minute to try and capture at the third column there. So you can imagine, say, if this Y had a the final attacker strategy left U11 at time, I don't know, 4 and went to U22, then here in the X strategy, the strategy where the police waits here forever would instead think, okay, so it's now time t equals 4, the final time t that the attacker leaves the first column. Assuming that the attacker does play that strategy, I know it's beneficial to move off my U21 and try and move to interdict the attacker there. I'm safe to move off because I know it's the final time. There's nothing else that's coming my way here. So that's why, so the police, he can move there and get some strictly better than 1/2 probability. And so that's a contradiction because Y was supposed to guarantee at most probability 1/2. if it was to be a Nash equilibria. So there is no finite support Nash equilibria in the continuous case here. And this is sort of like the essential example there. But we can, if we wanted to, we can try and approximate that infinite support Nash equilibria with finite and finite discretizations, at least for this example there. So now on to actually computing these things, these Nash equilibria. So given all the above, we can theoretically find Nash equilibria in those finite sets there. But in principle, they are way too large to enumerate. So they go up as the number of paths in the graphs, and it's exponential. So it's way too large to try and enumerate all of these. So the solution is this double oracle framework, which basically sort of iteratively adds more and more strategies to your sort of small space of strategy space until you reach sufficient convergence. So just to explain the concept a bit better, sort of a natural definition subgame Nash equilibria, where you only care about a subset of your actual strategy space. So if in A dash and D dash, you're a Nash equilibrium, a subgame Nash equilibrium within that A dash and D dash if you are with respect to those sets there. So I'm only caring about what's going on inside those sets. I don't care what happens outside. So the double oracle method looks like the following. So I begin with sort of small strategy sets, A dash and D dash. I can sort of get these from heuristics or the like. And then I'm going to repeat the following. So I can find a Nash equilibrium of my small sets A dash and D dash and find the payoff. So by the way, this is a very quick operation. I can do that with a very simple linear program. And then the meat of the double oracle is in these two oracles here. So finding an optimal attacker strategy against the current best mixed strategy, and then finding an optimal defender strategy against the corresponding Y there. So this is where the hard stuff is. And then if I made an improvement, then I add it to my strategy for both players, respectively. And then once I find no improving strategy, so if it's just happens that the optimal attacker strategy is as good or worse than that current V, then I know I can't do any better globally, and I can stop there. So we're gonna focus in on these two parts here. So this top one, finding an optimal attacker strategy against some mixed defender strategy, is called the attacker oracle, and the defender oracle is similar for the defender there. Sort of pictorially, if people like pictures, I start off with initial strategies. I go into the master LP. So this is very, very quick compared to the attacker and defender oracles there. If I have some strategy matrix M, which I can sort of keep a track of, that's going to be our binary matrix. I can always very quickly, using linear programming, find the optimal mixed strategies. But in between, I'm going to use these attacker and defender oracles and call them often to try and add to our strategy matrix M. And then once I'm satisfied with convergence, I know that I have a Nash equilibrium there. So that's that. And so we can look at what's happened in the past. So big M defender oracle, this was one of the first defender oracles to be made for this escape interdiction games. So it's a very big mixed integer linear program. And here it is. It's not that nice to look at, or beauty's in the eye of the beholder. But the thing I want to focus in on is the fact that the sort of bluish outlined area, that those constraints take care of the feasibility of the solution. So making sure that your attacker path actually is a path, a feasible path. And then the green bits just make sure that the objective is computed correctly. So in particular, there's this ZA variable, which is an indicator which is 0 if the attacker strategy is not interdicted, and 1 if it is interdicted by the strategy A there. And also I want to highlight that you do need a explicit upper bound on the number of resource states, so the number of defender states that they use. And that's not very nice to always enter in. And also it's using the delta, the discretisation parameter there. And then there's an analogous attacker oracle, very similar. Here's the big mixed integer linear program. And then once again, the blue bits ensure that it's a feasible path, feasible solution. And the green bits ensure that the objective, the probability of interdiction, is actually computed nicely. And then so our new network attacker oracles is based on a sort of time expanded network. So I'm still in the case where I'm assuming integral data and integral travel times. Remember, you can scale the data assuming it's rational, so you can get this. And then I'm going to create my time extended graph with sources and sinks, so dummy vertices there. And here's the sort of essence of the time expansion here. So that's my vertex set, where t half is sort of those half integer time points that was discussed earlier. And so there's my vertices here. This is still sort of the same example that we looked at like minutes ago, a smallish example here. And there's my time expanded network there. My edges are sort of natural to draw, so I have my source and sink sort of edges there. And then I draw an edge if I'm allowed to go from node U a time I to node V a time J. So I need that inequality to hold over there. And then finally, I'm allowing, so in a very classic sort of way of, I'm modeling these green edges as sort of like, I'm going to put costs on them so that I can detect when a police is on there or not. So, so once again, blue is taking care of that it's actually a feasible path, and then green is taking care of the probability of interdiction there. So there's my graph, and then I can see that a unit flow from my source to my sink is going to give an attacker strategy. And so here's my linear program here, probably much more nicer, hopefully. So once again, blue is taking care of feasibility, and green, this constraint here, is taking care that the probability of interdiction is actually computed correctly. So I have those binary variables there. And it turns out, so this is almost a shortest path problem. It's not because of this constraint here. The reason why we can't simply take all our current defender strategies and then just, whenever I see a node and a time that a defender is on, I add a probability to there. I sort of penalize that node, and then I'll just add across all of those defender strategies and find a shortest path using those penalties. I can't do that because of this, the following fundamental reason. It's that a single defender strategy may contribute to sort of multiple interdictions along the network. So if you remember back to our example with two resources, two police officers, there were some cases where an attacker could technically get interdicted twice. But we only want to count an interdiction once, so against a defender strategy. Given an attacker strategy and a defender strategy, either interdiction occurs or not. We're not counting multiple interdictions. So because of that, we do need this constraint here. We do need to not treat it as a shortest path problem, but instead as a sort of an explicit constraint like over here. And so this one variable is the obvious indicator variable if under strategy X, there is a resource on node V at time I. So that's my network attacker oracle as a linear program. Defender oracle is very similar. I create a time expanded network like the following. I draw edges like so, and once again, blue make sure it's feasible. Green makes sure that the probability of interdiction is computed correctly. And then once again, very similar to before, is I have my network flow constraints, and then this constraint in the same way as the attacker oracle, it makes sure that this Z variable is computed correctly. So Z means, or ZY means that my against strategy Y, I'm getting interdicted or getting an interdiction or not, indicator variable. So an advantage is I don't need any more Lmax, unlike those mixed integer big M oracles. And also I've broken resource symmetry in the defender oracle with just a single unit, single commodity flow, sorry. So I'm sort of treating all the police officers the same. And I can always create one sort of big dummy node R0, as my sort of starting point for the flow there. So we can think a little bit about these networks because there is a little problem. It's that this time expanded network size grows as this number increases. I sort of put that divide by delta there, even though we're going to soon assume it's always 1 by scaling accordingly. And so you can think about a single edge in the original network. So like so, say its distance is 3. In our time expansion, I might have to create this sort of huge gadget for this single edge. So all of these sort of middle edges would have to be drawn. And you can imagine if Tmax is really, really big, then I'd be drawing quite a lot of these edges. And actually, so really bad. So some of the benchmark instances that we tested this on, the worst one had like around 100 million arcs, which is about the time when like the solver really struggles. So it's not very nice. So we can improve this though. The insight is our oracles, they get to assume that the other player is already playing some strategy, some mixed strategy. So I'm going to, for argument's sake, I'm going to assume that we're in the attacker oracle, and I get to assume that the defender, they have a police there, so at node U at time, say t+4, and also at the same node U, but at time t+7, and no police in between those 2 times. So just say that's in the mixed strategy as of current. So now if you think about it, I don't need to travel along any of the gray edges. So say this one over here, the second edge, if I went there, then the only reason I would want to go there instead of just first max speed travel along the first edge is, well, there's no point, because if I was to travel the second edge, I would get hit by the police over there, but and I might hope to escape using that node there, so U t+4, and escape somewhere else. But I could have done the same thing is if instead I just went quicker in the first place and left at time t+3 instead, and completely evade the police over here. So there's no point in me traveling along the second arc. There's also similarly no point in me traveling along this the 4th and 5th arcs because of the sort of same reason, but applied to this 3rd arc here. So if I was going to travel along one of those, the 4th or 5th arc, I should have done it along this 3rd arc. So I'm using the 3rd arc because maybe I want to go after this this police leaves over here. And so I should always choose to travel slower, departing from t+5, than going along the gray arcs here and departing there. So the big thing is I only need to draw these, I call them opportunistic nodes and arcs, given that I get to assume the other player is playing some mixed strategy. And so I can do a similar thing with the defender oracle as well. I only need to draw the necessary arcs that actually come just before, just after some key events happens, assuming the other player is playing some fixed mixed strategy as of current. And oh yes, and if you think about it more, I can even get rid of entirely that ut+6 node because it's completely useless, because I should either just wait to move slower, depart from t+5 and move slower to my next destination, or I should just wait even longer and arrive at u at time t+8 over there. So very nicely is now this time expanded network size, it doesn't grow not directly as to Tmax divided by delta, but now it's really a function of the other player's support size and like the size of the strategies within that support. So, and that's sort of all to do with how many of these red arcs I have to see. So that's very nice. And then that got a really big reduction in some of the worst benchmark cases. Only 10,000 arcs in that other case that was previously stated over there. So just a refresher of what was going on with the double oracle. I have initial strategies. I have my master LP, which computes the optimal mixed strategies given my current matrix M, which contains the sort of strategies as of current. And then the attacker oracle and the defender oracle are going to create or generate new best responses for each of those. And so our computational results, we looked at sort of 80 benchmark instances, 10 instances for every single square grid size from 3x3, 4x4, so on, until 10x10. So here's a typical example on the right there. And we compare sort of between three different algorithms. So one was the big M oracles that we saw earlier. There was big mixed integer linear program formulations. And I did a fresh like Julia implementation, Julia the programming language. And then there was a meta heuristic by Samantha et al. And their results were taken directly from the paper, so I didn't do any implementation with that. And then finally, our new network oracles, also using Julia. So all in the same program. And where we used Garobi to solve all our mixed integer linear programs. So there's only there's three problems. So the master LP, attacker oracle, and defender oracle are the key players there. And so we did that. And then here's like one of our key plots here. So us is the blue dashed line, so a network. And this is so the cumulative percentage of problems solved against runtime. So here, it's a very steep, near zero, but it's steepest for us network. So we solve quite a lot of the those benchmark problems within about 10 seconds or 20 seconds or so, or at least 100 seconds if you want to be safe or something. And then as you get more time, so we solve a little bit more, but there is a tiny gap between us and the heuristic there. So there was only 2 instances where we didn't converge within the 1 hour time. So there was a 1 hour time limit put on all of these. And the big M oracles, they were not as good. So they only could solve to completion less than a quarter of the problems there. So there's our result there. And then just in comparison with the objective error that the heuristic could get between our sort of exact algorithm, our network algorithm there. So here, it's a histogram of the error, error from the meta heuristic minus our actual result. And so this dashed line here is all the instances where the heuristic got it correct. So it was the actual correct answer. And then all these other ones are the sort of error, the error cases there. So there was 4 cases up here with error 1, which is the maximum possible error in an EIG. This is when we said, so the network oracle came up with which way does it go? Say one player had a winning strategy, so say with objective 1, but the heuristic claimed that it finished and it said that there was not a winning strategy, and it was actually the other way around, that the other player had a winning strategy. So there was 4 cases like that there. Yes. And then so these other results, these sort of give us sort of 2 bits of information. It shows us so the full here, so looking at the left, this full means sort of the attacker and network, the defender network, where we draw all of the arcs, all of the nodes. So how big does that problem get, and how long does it take to run, versus the support based. So the one with the improvements, so only drawing the opportunistic nodes and arcs, what their runtimes look like, but also sort of the distribution of calls that had to be made. So I did do another run with just the full networks and tried to see how they perform. And you can see, the blue bits are always mostly to the right of the orange bits. The orange bits are the support-based opportunistic arc ones, and the blue bits are the completely draw everything networks. Yeah. Oh yeah, it's basically done. Yeah. And so future work. So I didn't really talk about, so how does real data EIG fit into this? So we know like classical like network flow problems, classic like Ford-Fulkerson algorithm can get a bit hairy with real data network flow instances. And also, how complex can these Nash equilibrium be? But also specifically, like, can we actually find a neat sort of mathematical characterization of escape interdiction gain Nash equilibria? And also, on top of that, can we find an actual algorithm without the discretization? So is there some continuous game theory that you can pull and get you some algorithm that can not care about the discretization? I'm not sure. I think that's all, yes.